Hello everybody. In our previous video, we learned to find the area between two curves. In this video, we are going to concentrate on one of the simplest applications of integration, which is called volume of solid revolution. We are going to learn 3 different techniques and then we solve questions to understand it better. The first technique we are going to start with is called the disk method. Now imagine that you have the curve y equals f of x, which is continuous on the interval AB, and the region between this curve and the line y equals c when x changes from A to B is revolved about the line y equals c. Then the volume of the solid, which we generated by this revolution, look at this. This is the solid we generated. And by the disk method, the volume of the solid is given by the integral from A to B pi times r squared of x dx. Now, what r is basically the radius of the circular disk. Now, let's take a cross section here. As you can see, our integration variable is x. That's why I call this point x. And as you can see, since this point is on the curve y equals f of x, the corresponding y coordinate will be f of x. This is the radius of our circular disk. And as you can see, it is equal to f of x minus c. So this formula becomes pi times integral A to B f of x minus c squared dx. Now be careful that instead of revolving about the line y equals c, if we revolve it about the x-axis, then it means we are revolving it about the line y equals 0, which means c is 0, then your formula becomes f squared of x dx. Now, with a similar motivation, actually take a curve x equals g of y, which is continuous on the interval c, d, and let's revolve it about the line x equals a. Then the solid we generate is this. Again, our formula this time will be pi times c to d integral r squared of y dy. Again, r is the radius of the circular disk. What we do, we take a cross section, and then this is the radius of the cross section. As you can see, our integration variable is y. So if I call this point y, the corresponding x coordinate, since this point is on your curve x equals g of y, will be g of y, and your r will be g of y minus a. So g of y minus a squared dy. Now I want you to pay attention that actually when we are using this method and we revolve it about the line y equals a constant, our integration variable is not y. Our integration variable is x. And similarly, if we revolve it about x equals a, then our integration variable is y. Let's solve a couple of examples. The first example is actually we are taking the region between the curve y equals square root of x when x changes from 0 to 4 and the x-axis. This is our region, and now we are going to revolve it about the x-axis. And if we use this method, the solid that is generated by this revolution will be this one, and if I express it as v sub y equals 0, since the x-axis is represented by y equals 0, first of all, since we are going to use This method, let's replace that pi here. Now remember, when this is y equals something, our integration variable is x. Let's replace it here. Let's look at our region, look at our solid. As you see, the x variable changes from 0 to 4. That's why our integral changes from 0 to 4. We take a cross section. This is the radius of our circular disk. We know that everything must be in terms of x, so I call this point x. This point is on our curve y equals square root of x. That's why the corresponding y coordinate will be square root of x. And as you can see, the radius of the circular disk is square root of x. So here we write square root of x squared dx will give the volume of this solid. Now, the second example, let's take a different region. This time our region is between the curve y equals square root of x, where x changes between 0 and 4, and the y-axis. Now, we are going to revolve it about the y-axis. Actually, the solid we generate will be this. Now, let's write our integral by using the disk method. Now, we are revolving it about the y-axis, which is the line x equals 0. So, v sub x equals 0 pi times integral. Now, because the revolution line is x equals a constant, our integration variable will be y. Now, as you can see, the y coordinate changes from 0 to 2. So let's write it here. The only thing we need to decide is the radius of the circular disk. Here you go. This is the radius of your circular disk. Now we know that everything must be in terms of y, so I call this point y. This point is on our curve y equals square root of x. Or in other words, x equals y squared. So the corresponding x coordinate will be y squared. And as you can see, the radius of the circular disk is y squared. So our integrand will be square of y squared dy. This integral, if we evaluate it, will give us the volume of the solid. Now, let's look at this third example. This time, we have the same region, but we will revolve it about the line y equals 2. Actually, this is the solid we will generate. And again, if we use this method, the volume of the solid, when we revolve it about the line y equals 2, is pi times integral. Let's decide the integration variable. Since this is y equals a constant, our integration variable is x. And as you can see, the x coordinate changes from 0 to 4. Now we need to decide our radius of the circular disk. Here we go. I take a cross section. This is the radius of the circular disk. Now everything will be in terms of x, so I call this point x. The corresponding y coordinate will be square root of x. Now be careful. The radius of the circular disk, since this is 2 units and this much is square root of x, your r turns out to be 2 minus square root of x squared dx will give you the volume of this solid. Now let's take a look at this example. Now this time they give us the region as bounded on the left by y equals square root of x, on the right by this line y equals 6 minus x, and below by the x-axis. Here is your region. Before you calculate anything, you need to find the intersection points, and we have already learned how to find the intersection points. Now, if we calculate it here, we need to find the x and y coordinates which make both of these equations a true statement. So I said square root of x is equal to 6 minus x. take the square of each side, then you will get 36 minus 12 times x plus x squared, which gives you the equation x squared minus 13x plus 36 equals to 0. Now we need to think about two numbers whose sum is going to be minus 13, whose product will be 36. Then we have x minus 4 times x plus x minus 9 equals 0. As you can see, multiply them, you get 36. Add them, you will get minus 13. So here are your points. X equals 4 and x equals 9. Now when you look at your region, you can easily see that 9 is not in your region. That's why the intersection point is 4. Now if we revolve this region about the x-axis, actually we will get the solid. We will generate this solid. The reason why I really want to add this example here is that you need to be careful about your bounding curves. Now, the bounding curves actually change. So this will create two solids, two pieces of solids. So what we will do is, first of all, we calculate the volume of the solid on the left-hand side, then we will calculate the volume of the solid on the right-hand side. The reason is because our radius of the circular disc will change. Now let's take a cross-section. This is your R, and as you can see, when we revolve it about the x-axis, or in other words, y equals 0, we know that everything must be in terms of x, our integration variable at least. Now, if I call this point x, this point is on the curve y equals square root of x, so the corresponding y coordinate will be square root of x. This time, r is equal to square root of x, so I will write here the square of the square root of x dx. And this r is only valid when x changes between 0 to 4, so I write it here. Now, what we have done, actually, we calculate the volume of the solid. Now, we need to add the volume of the solid, which is on the right-hand side. So I say right here, pi times integral, again, our integration variable is x. Now, as you can see, the x-coordinate changes from 4 to 6. Take a cross-section, this is your r, call this point x. Now the corresponding y-coordinate, since this point is on the line, will be 6 minus x. So your r is 6 minus x. So 6 minus x squared dx. So the sum will give you the volume of the solid. But what if we revolve this shaded region about the line y equals minus 1? Then we will generate a solid where there is a hole in it. Then we need another method, which is called washer's method. Now, if the region we revolve does not border on or cross the axis of revolution or cross the line of revolution, then there is a hole in the solid. Then we use washer's method, and washer's method tells us that if you revolve it about the line y equals c, the region between the curve f and g, it is equal to pi times integral a to b capital R squared of x minus r squared of x dx. Now here, r is your outer radius, and this r is your inner radius. Now, outer radius is the distance from the outer curve to the revolution axis, whereas the inner radius is the distance from the inner curve to the revolution axis. So in our case, this is our outer radius, and this is our inner radius. Now, if we revolve this region about the line y equals c actually we will see a solid which looks like this. Basically, what we use to obtain this formula is nothing different than the disk method. First of all, we assume that there is no hole in the solid. We calculate the volume of the total solid, and then we subtract the volume of the hole. Similarly, if you have a region like this, and if you revolve it about the line x equals a, again, you will have a hole in the solid. With the similar motivation, the volume of the solid will be pi times integral c to d r squared of y minus r squared of y dy. The outer radius and the inner radius. Okay, that's the only thing you need to decide. Now, if we go back to our examples, let's start with the original one, where we end up with a problem. Now, we are revolving it about the line y equals minus 1. Okay? So this is equal to pi times integral. As you see, y equals a constant is our revolution line. That's why our integration variable is x. And when you look at your region, which is this shaded region, your x-coordinate changes from 0 to 4. So the only thing you need to decide is your outer radius and inner radius. Now we know that everything will be in terms of x. Outer radius is the distance from the outer curve to the revolution axis. So here is your outer radius. Now call this point x. The corresponding y-coordinate will be square root of x. Now your outer radius is square root of x plus 1 unit. That's why I write here 1 plus square root of x squared minus. Now I must take the volume of the hole from this value. That's why I need to calculate the inner radius. Now, as you can see, the inner curve is the x-axis itself. So here is your inner radius. Remember, the x-axis is the line y equals 0. So your inner radius is fixed, which is 1 unit. So we write here 1 square dx will give you the volume of this solid when you use Washer's method. Similarly, we can look at this example too. Let's revolve this region, but this time let's revolve it about the line y equals 2. Again, since the curve does not border on the revolution line, there will be a hole in the solid. That's why we need to decide the outer radius and the inner radius. So let's write it. V sub y equals to pi times integral. Since this is y, everything will be in terms of x. As you can see, x changes from 0 to 4. Now we need to decide the outer radius. If you call this point x, this point is on this curve. That's why the corresponding y-coordinate is square root of x. And let me also show the inner radius, which is this one. Now, as you can see, the outer radius is the distance from the x-axis, which we can also show by the line y equals 0, to the revolution axis, and that is fixed. R is always 2. So we write here 2 squared minus, now we need to decide the inner radius. This is 2 units, this is square root of x. That's why the inner radius is 2 minus square root of x squared dx will give us the volume of the solid generated by revolving this region. Now, let's look at this example. This time our revolution axis is x equals 4. And as you can see, the region does not border on the revolution line. That's why, again, there will be a hole in the solid. So if we write Vx equals 4 pi times, we already know that the integration variable must be y. And as you can see, your y changes from 0 to 2. The outer radius is the outer curve, the distance from the outer curve to the revolution axis. So here you go. This is your outer radius. Whereas this is your inner radius. Now we decided that our integration variable will be y, so let's call this point y. This is on your curve, so we can write this curve as x equals y squared, so the corresponding x coordinate will be y squared. Now the outer radius is again fixed, which is 4 units, so this is 4 squared minus the inner radius is 4 minus y squared. So that's the integral we get, which gives us the volume of this solid. The last method we are going to learn is called shell method. Consider this curve y equals f of x, and the region between this curve and the x-axis when x changes from a to b. Imagine that this region is revolved about the line x equals c. Then the solid we generate will look like this. Now with the shell method, the formula which gives the volume of this solid is 2 pi times integral a to b shell height times shell radius dx. Now I want you to be careful. Now when you're revolving about the line x equals c, your integration variable is exactly the same with this one. So that's the main difference between the disk method, including washer, and the shell method. So what is our shell height and shell radius? To get the value of shell height, what you will do is you will look at your shaded region, you draw a line segment parallel to your revolution axis, which stays completely inside your region. So here is your shell height, and the distance from the shell height to the revolution axis is called your shell radius. With a little motivation, of course, you can obtain a similar formula when you revolve this region, when y changes from c to d, and if you revolve it about the line y equals a, then again, shell height times shell radius won't change, but of course depends on your curve and depends on your integration variable. These will have different expressions. Now, let's go back to our previous example. The first question we solved was this. We used disk method and we find that the volume of the solid will be evaluated with this integral. Now, pay attention that this is x, right? If we solve it, which is very easy, so I'm going to solve it. This is pi over 2 times x squared when x changes from 0 to 4. So first the upper limit 16, so 16 over 2 is actually, the volume of the solid is 8 pi. But now I'm going to find the same volume by using the shell method. Let's remember, we are revolving about the line y equals 0 or the x-axis. What I'm going to do, this is my revolution axis. I draw a line segment parallel to the revolution axis, which is my shell height. And the distance from the shell height to the revolution axis is your shell radius. Now, if I write the same volume, but this time using shell method, I must replace 2 pi here first of all. I know that the integration variable is y. And when you look at your region, you will see that your integration variable changes from 0 to 2. And since everything must be in terms of y, I call this point y. This point is on the curve y equals square root of x, or in other words, x equals y squared. That's why the corresponding x coordinate will be y squared. So actually, your shell height is 4 minus y squared. And your shell radius is, which is this, is equal to y. So y dy will give you the volume of the solid if you use shell method. Now actually when you look at here, the integrand is 4 times y minus y cubed. And when you integrate it, you will get 2 pi times 1 over 2y squared. So 2y squared minus y to the power 4 over 4. When y changes from 0 to 2, let's write the integration limits. 2 squared is 4, 2 times 4 is 8, minus, if you look at this, this is 4, minus, when you replace 0, you will get 0. So again, you will get that the volume of the solid 8 pi. It doesn't matter which method you use, you will always find the same answer if you do it correctly. Now, let's look at this one. We found before that the volume of the solid with the disk method is evaluated with this integral. Now, let's use shell method. What I'm going to do this time, my revolution axis is y-axis, which is the line x equals 0. Let's draw a line segment inside our region, which gives us the shell height. And the distance from the shell height to the revolution axis is your shell radius. So, the volume by the shell method is 2 pi times, now remember this is x, that's why this must be x. And as you can see, on your shaded region, your x coordinate changes from 0 to 4. Everything must be in terms of x, so I call this point x. This is on the curve y equals square root of x, so the y coordinate will be square root of x. And as you can see, your shell height is 2 minus square root of x. And your shell radius is x. So this is the volume with the shell method. At this point, I want to point out that when you draw your shell height, make sure that it won't change, no matter where you draw it in the shaded region. If it changes, then you need something else. Now, let's look at this one, the last example. This time we are revolving this region about the line y equals 2. We know that with the shell method, 2 pi times the integration variable is y. So this time I will draw a line segment parallel to the revolution axis. Here is your shell height. The distance from the shell height to the revolution axis is your shell radius. Again, look at here, everything must be in terms of y. So I say that this point is y. Now this curve can also be written as x equals y squared, so the corresponding x coordinate is y squared. Now your shell height is y squared. And your shell radius is, be careful, it is 2 minus y dy. And your y coordinate changes from 0 to 2. So that will give you the volume of the same solid. In this video, we learned how to find the volume of a solid. We learned 3 different methods and we solved several examples. What I will advise you to study a lot more than this and solve additional examples. I hope this video will help you in your studies.